Okay, so last time we talked about the compliance matrix. And if you have the compliance matrix, you always can get the stiffness matrix. Your calculators just do it as, just get that matrix, raise it to the power of -1, and it'll compute that inverse for you. It's great. Okay, so let's do an example. Where let's say we have a tensile test of a material. This is sort of like a two-part example problem. And that tensile test, so here's our sample piece. We put it into 5,000 newtons of tension. Before the deformation, the dimensions are 2 centimeters this way, 10 centimeters this way, and 1 centimeter this way, not drawn to scale. And when we apply this 5,000 Newton tension, so the loaded deformations, well, I guess they're not deformations, they're loaded dimensions. That length, I'll call it length, width, thickness. The length is 0.10003. And the width, does it make sense that the length gets bigger in this tensile test? Okay, and what's going to happen to the width? That originally 0.02 meters, is that going to get bigger or smaller? Smaller, yep. And so that is 0.00, oh no, I guess I measured the other. It's the one that was initially 1 centimeter, I guess. But that one also gets smaller. 0.0099, there's 4 nines and then a 2. Okay, so that's our tensile test. And then the next day, after we have a nice breakfast and a restful sleep, the stress at a single point for that material is 2 times 10 to the 7th, -1 times 10 to the 7th, 0, -1 times 10 to the 7th, 0, 0, 0, 0, 8 times 10 to the 6. And that's all just in pascals. And the question is, what's the strain? We'll do the Voigt strain at that point. Okay, so what we're going to do is we're going to use this tensile test to figure out E and nu. And then we're going to plug that in, get a compliance matrix out of that. And then we're going to use the compliance matrix to figure out the strain associated with this stress. You with me on that? So this is like, this is a very practical application. Like, say that you have this new filament for a 3D printer or whatever. So you do this tensile test, you figure out you have to be careful with 3D printers because it's not really isotropic, but you can sort of approximate it that way. Why isn't a 3D printer...
The layer lines.
Yes, exactly. Exactly. So it's 3D printed stuff is stronger in one dimension,
FDM.
What?
I was gonna say FDM. Have you heard of like SLS 3D printing?
Oh no.
Where it's it levels over like layers of powdered metal, and then it lasers them together, and then you put it in an oven afterwards.
No.
Or like UV resin printing, where they actually 3D print upside down, so it submerges the build plate upside down in a bowl of resin, and then it shoots a laser at the build plate, which cures the resin.
Wow.
Shape. And that's...
No. Every practical thing about engineering I've ever learned, I've learned from you guys in class. Okay, but anyways, so, if you 3D print something, you could do this tensile test to figure out E and nu, and let's just say you have to be careful about assuming isotropy, but and then once you have that, you can come up with this compliance matrix and relate stresses and strains based on your tensile test. Okay, so let's use the tensile test first. I'm going to call the I'm going to call X this way, Y this way, and Z this way. So the two measurements that we have are the X and Y dimensions. And so let's start by figuring out the XX stress. So that stress is the tension divided by the cross-sectional area. So that's 5,000 divided by, what's the cross-sectional area of this? Well, it's going to be 0.02 times 0.01. And so that is 5,000 divided by 2.0002. And you get 2.5 times 10 to the 7 pascals. And now let's figure out the strain, the XX normal strain. So this is the deformed X length, 0.10003. Minus the starting length, 0.1, divided by 0.1. And this comes out to be 3.0 times 10 to the minus 4 pascals. Are we concerned about the size of that strain? It's getting up there into the ballpark of where we might be a little skeptical about it, but it's probably fine,
Which one is?
The fact that this strain is bigger than 1 times 10 to the minus 4, that's...
What about the one before it?
That's a stress.
Okay.
Yeah.
Yeah, the stresses are big, right?
Right. That's bigger than 1 times 10 to the minus 4. Yeah. But the strains are where we determine whether it's small deformations appropriately, 1 times 10 to the minus 4, all I'm saying is that's not like a hard and fast rule. That's just a total rule of thumb. If it's way bigger than that, then you know that you can't trust it. And then let's calculate strain YY. That is equal to 0.0049 and a 2 minus 0.01 divided by 0.01, and you get negative 8.0 times 10 to the minus 5. Oh, and I wrote units of pascals on that strain. Strain is unitless, so don't put that there. This is just a number. All right, and so now we can use the formulas to calculate E. E is equal to the XX stress divided by the XX strain. So that's 2.5 times 10 to the 7 pascals divided by 3.0 times 10 to the minus 4. And you get 83.3 repeating times 10 to the 9 pascals. That stiffness is somewhere in the ballpark of like copper, you know, like a softer metal. The one we'll use all the time is steel. That one has a value of 200 times 10 to the 9. And now the Poisson's ratio. The formula for that says negative off-axis strain, and in our case, the off-axis strain that we know is EYY, divided by EXX, the on-axis, loading axis strain. So this is negative 8.0 times 10 to the minus 5th, and then negative of that, divided by 3.0 times 10 to the minus 4. The negatives cancel. You always need to get positive numbers for your Poisson's ratio. And this comes out to be 0.26 repeating. And since this is unitless divided by unitless, this Poisson's ratio is unitless. And I said, if you don't know Poisson's ratio, with engineering materials, your best guess is just 0.3, and that's usually a reasonable guess, and this is close to 0.3. And now that we have this, we can fill in the compliance matrix. You should take the time to get this entered into your calculator as a program. On Wednesday, we'll spend some of class just making sure that this is working in your calculators. But basically, you want to do something like you want to have a program or a function in your calculator. I'm not going to go through it right now, but if you go to the course materials in D2L, there are programs written there that you can enter into your calculator. So try to get that working. If you can't get it working, we'll get it working on Wednesday, okay?
Would you say it should output a matrix?
Yes,
So
exactly.
you just, like, kind
It
of
should output
multiply
a
that
6 by,
function by
yeah.
another matrix?
Yes, exactly. Yep. And so the compliance matrix is 1 over E, negative nu over E. I'm not going to fill out this whole thing this time. Negative nu over E, 0, 0, 0. And then it keeps going down until the last row is 0, 0, 0, 0, 0. and then 2 times the quantity 1 plus nu over E. And so if you plug in these values for E and nu, you get this matrix. This one I am going to fill out just numerically. So you get 1.2 times 10 to the minus 11, negative 3.2 times 10 to the minus 12, negative 3.2 times 10 to the minus 12, 0, 0, 0. Then negative 3.2 E minus 12, positive 1.2 E minus 11, negative 3.2 E minus 12, 0, 0, 0. Then negative 3.2 E minus 12, negative 3.2 E minus 12, 1.2 E minus 11, 0, 0, 0. Then 0, 0, 0, 3.05 E minus 11, 0, 0. Then it moves over one spot. And then it moves to the last spot. Nope. So based on that tensile test, this is the compliance matrix. So how do we get the strain, the Voigt strain out of this? We put that stress tensor in the Voigt form and then multiply the Voigt stress to this compliance matrix. You guys need more time to write down these values.
We probably don't even need it, but
That's a bad attitude. Oh, does it make sense that we have tiny values? This is always good sort of sanity checking stuff to think about in your head. You're going to have all these big numbers, like look at your numbers and say, does this make sense with what I expect? You expect your stresses to be big. You expect your strains to be small. You expect your compliance matrix to be big or small. You expect it to be small because remember I said the thing about if someone chucks a hunk of steel at you, do you think like, that's so compliant? No, compliance is very minimal. Okay, so the Voigt strain then is equal to that compliance matrix times the Voigt stress, which I gave you it in stress tensor form before. To put it in strain, take a second and look at that stress tensor and put it in the Voigt strain, in the Voigt stress. Just get used to translating these back and forth. Voigt stress is the EE normal stress, the YY normal stress, the Z normal stress, 8 times 10 to the 6. Now the YZ shear stress, the XZ shear stress, and the XY shear stress.
Follow the right triangle.
And now if you multiply it by this compliance matrix, you should get 0.000214 negative this point 4 zeros, 1, 2, 3, 4, 9, 0. And then 0.4 zeros, 3, 2. And then 0, 0, and then negative 0.000304. Okay, so let's think about what these values mean. So along the x-axis, is this thing stretching or contracting?
Stretching.
Yep. Along the y-axis, is it stretching or contracting? Contracting. And z, stretch. Nothing for those two. And then here, this is the XY shear stress. So the positive X and positive Y face angle, is it getting more acute or more obtuse? Acute.
So you can think of it, yeah, as like what's happening to the angle.
Yes, right. And so you could, I mean, I don't make you spend a lot of time doing this stuff, but you could think of this as, so like, what do we know about, I'm just going to draw it in the XY. So we're not going to see that Z stretch, but you could think of that as it's getting longer along, no, that's not X. Stupid. It's getting longer this way. It's getting shorter this way. The positive X and positive Y faces meet at an angle over here. That's getting acute. And so we have a shape like this. You know, gets longer along X, shorter along Y, and I didn't really make it shorter along Y.
What did you call that? A parallelepiped?
Well, yeah, this is a parallelogram if you're looking straight at one face, and the thing with every side being a parallelogram is called a parallelepiped. But it's nice to know that you can always visualize from the Voigt strain, you can always visualize what the deformations look like this way. Is this a pretty realistic version of, like, pretty realistic image of the size of the change? Not at all. You know, the difference, the fractional difference in the size of the lengths needs to be on the order of 1 × 10⁻⁴. Those angles in radians need to be on the order of 1 × 10⁻⁴. So you wouldn't even really be able to see it with your eyes, but this gives you an idea of the trends, you know.
So in this problem, you said the next day we measure the stress at a point.
Yeah.
Is that like a thing you can just do? You know what I mean? Like, how would you actually...
Okay, so first you're like, we're going to do this engineering analysis with this new material, you know, this new alloy or whatever. And so we have to do this tensile test, and you get all the information you need from the tensile test. Then whatever kind of actual engineering analysis you're going to do through finite elements or whatever, you calculate that the stress at some key point is this, you know, using some kind of calculation or whatever.
Sure.
And then,
would that be kind of like what we were doing? Like, is that related to internal loads?
yeah, I mean, we will end up using internal loads. It's kind of like the next level of analysis after internal loads. Yeah. Any other questions about this?
You'd use some kind of like density tester or something?
To calculate the stresses? Well, really, usually you, there are some ways that you can measure using load cells and stuff. That density idea, I mean, I think you couldn't, that's a good idea, but I don't think you could get directions with that.
Right.
you know, you could only sort of get volume change, but that's good thinking. Pretty much it just comes from calculations, you know, and after we're done with this, all this preliminary stuff, relating stresses to strains, what the different matrices are, then we'll spend almost the rest of the class just talking about how you would calculate the stress if you have a beam that's this rough shape and you load it like this, it has these internal loads. How do you go from that to a stress analysis? Okay, so now the next thing we have to talk about is stress transformations. And what this means is, given a stress tensor in one coordinate system, what's the equivalent state of stress in a new coordinate system? So a stress transformation is just re-expressing a stress in a new coordinate system. Okay, to make sense out of it, think about doing that with vectors. You're very used to that idea. So it's the tensor equivalent of, so, you know, if you have a coordinate system like this, let's say this has a length of 10, so I can do this in my head. Those vector components, let's call this vector u, is 7.66, 6.43. Okay, that would be if this was 40 degrees. Okay. Now that same vector, we haven't changed that vector. Well, I'm gonna be fancy. God. Okay, so we haven't changed that vector, but its components are different if the coordinate system is different. So now let's say we want to express that vector in this coordinate system. The vector hasn't changed, but now the components are 10, 0. Okay, you're used to doing that. It's not as intuitive to think of what it means with a tensor, but it's the same idea. We have a set of values that represent the tensor in one coordinate system. We just want the set of values that represent it from a different viewpoint, kind of. Okay.
Kind of just think of it like rotating the cube.
Yeah, so you can think of it as you're rotating the cube, and then you're re-expressing the traction vectors on the rotated cube in the new coordinate system too. So we'll see that it sort of it's a two-step process instead of a one-step process like this. You have to rotate the cube, and then you have to rotate the traction vectors. Okay, so to do this, we're going to use rotation matrices. You've seen these in 2D and statics. So first, if you are going to rotate the coordinate system, I stress this a lot in statics, but remember that every rotation we're talking about is a rotation of the coordinate system, not a rotation of the object in the same coordinate system. Okay, so this is a rotating the coordinate system theta counterclockwise about the x-axis. The rotation matrix that does that is capital Q, and it's equal to 1, 0, 0, 0 cosine theta, sine theta, 0 negative sine theta, cosine theta. Okay, second, what about rotating the coordinate system counterclockwise about the y-axis? Q is equal to cosine theta, 0 negative sine theta, 0, 1, 0, sine theta, 0, cosine theta. And then third is a rotation of the coordinate system about the z-axis. So let's say we're rotating the coordinate system counterclockwise an angle of theta about the z-axis. This rotation matrix is cosine theta, sine theta, 0, negative sine theta, cosine theta, 0, 0, 0, 1.
So are these true for both directions, but any axis?
Yeah, so just if it's clockwise, it's negative.
Okay.
Just put in a negative theta. And notice that you look at this and you're like, oh, your first glance is, it's a pattern that makes it easy to remember. And it kind of is. There's just one thing you have to be careful of. So the row and column associated with the axis that the rotation is around has a 1 in that kind of principal spot and then zeros. And then besides that, look at this, cosine, sine, negative sine, cosine. Look at z, cosine, sine, negative sine, cosine. Then look at y. Y always has to be difficult in everything. Cosine, negative sine, so it switches. Sine, cosine.
So it's like transposed.
Yeah, yep. And it's the same thing with cross product, same thing with everything. Y just always has to act a little bit better than everyone else, you know. I don't know why it always sticks with me, but this is how I always think of it. Like, I talked to somebody do you know who Gillian or Gillian Anderson is from X-Files? The actress?
Is she
She's Scully. Yeah, and or Mulder, Scully. Yeah, so I talked to somebody who went to high school with her, and she's like, oh my God, nobody could stand this girl. She's like, her family took a trip to England one summer for like a month, and she came back and spoke with a British accent for the whole school year. And I'm like, that's Y in person form. Gillian Anderson is like the Y-axis.
higher than everyone else?
Yeah, exactly.
Self-important. It's a good show.
Really good. Okay, so how does it work with vectors? Let's think of it. So let's first see it work with vectors. So I guess let me use the example I just used here. So let's say in this coordinate system, this vector has a length of 10. So it's easy to figure out what the components are of this vector in this coordinate system. It's just 10 along x, 0 along y. So this vector u is 10, 0. Okay? Now we want to use this rotation matrix idea to express this vector in the coordinate system like this. And I'm just going to have to tell you this angle is 40 degrees. Okay, so how do we do that? Well, you have to think we're starting with this coordinate system. And we're going to this coordinate system. So first, I guess, think about the axis that this coordinate system is rotating around to do this. Z, yep, so we know it's a rotation about Z. And then is it clockwise or counterclockwise about Z? It's clockwise, so this theta is negative 40.
Does it matter which way you're looking?
Yes, that is, yes. You're in 2D, you don't have to think about that kind of stuff. In 3D, whether something's clockwise or counterclockwise always depends on how you're looking at it. So in every case here, you need to be looking at the arrow. The arrow is pointing towards your face when you look at it, to think of clockwise
So
and
you want to be
counterclockwise.
like standing on the positive side.
Yeah, right.
Isn't that the opposite of how we did theta and statics?
Nope,
It isn't?
no.
So, but I suppose we were doing it along the z-axis, right?
Right, always along Z. Now we have other ones we have to worry about too.
Still follows the right hand.
Yeah. Okay, so this is,
Remember to be positive.
but I did say in statics that one thing you always have to be careful about anytime you use rotation matrices. So when you do it, you're just always going to be rotating the coordinate system. If you're communicating with someone else, you always have to be sure that you're not talking about different types of rotations. Because if they're talking about a rotation of an object, keeping the coordinate system fixed, all their angles are opposite of yours. And they're using a different type of rotation matrix. So it's kind of a mess, and you just have to be really careful about it. Okay, so that means that our Q is going to be cosine of negative 40, sine of negative 40, 0, negative sine of negative 40, cosine of negative 40, 0, 0, 0, 1. And so that is 0.766, negative 0.643, 0, positive 0.643, 0.766, 0, 0, 0, 1. And now our new U components are going to be Q times U old and so that's I guess I'll write it again. 0.766, negative 0.643, 0, negative 0.643, 0.766, 0, 0, 0, 1, times our original vector components, which were 10, 0, 0. And if you multiply this, you get 7.66. This, I have a negative here where I shouldn't have. 6.430, which is what we expected.
When we have 0 in the z-axis, can we just leave it out depending on the problem, or would you generally just include that to show that there's...
You have to include it in Deform because everything's going to be 3D tensors. But with vectors for sure, yeah. And this is another one. So I just said you want to get the compliance matrix in your calculator. You also want to get a program in your calculator for the rotation matrix where you just enter, so basically some version of like you enter which axis you're rotating about, what the angle is, and it spits out the rotation matrix. Okay. Because you don't want to be filling out 3x3 matrices over and over again.
Can you put logic in those functions?
Yeah, you can. You also, I think...
How good of a calculator do you need to do that?
No, to do, like, if-then you're talking about, right?
Yeah.
Yeah, so
Like
if
that.
the axis is 1, then the matrix is this. If the axis is 2, then the matrix is this. But another maybe quicker way to do it is just have 3 separate functions, one called rot x, where you just plug in the angle, one called rot y, where you just plug in the angle, that kind of thing. Okay, don't leave yet. This is the punchline. So you can use these same rotation matrices. I'll tell you when you can leave. To express a stress tensor in a new coordinate system. And the way it works is the new stress tensor is equal to Q times the old stress tensor times Q transpose. Okay, you can leave. So so one of those Q's, think of one of those Q's as rotating the cube and one of those as re-expressing the tractions. So with vectors, we only had to multiply once. With tensors, we have to multiply twice. One is a transpose.
So why do you need to re-express the traction vectors?
Well, think of when you multiply by an outward facing normal to come up with a traction vector, it's still representing those components in your old coordinate system. So now you have, so basically the first one re-expresses all these traction vectors, but it's still you're kind of half in the new, half in the old coordinate system. Now you have to re-express those results in the new coordinate system. And that's what the two different ones are. So let me write that down. So one rotation matrix rotates the faces of the stress cube. The other re-expresses the tractions in the new coordinate system. And one kind of thing to notice, this is the last thing I'm going to say here. So what is that transpose doing? I mentioned this when I was talking about types of matrices. Remember that rotation matrices are a type of matrix called orthogonal. If you look at the columns, they're perpendicular, mutually perpendicular vectors. So rotation matrices are orthogonal matrices. And that means that the inverse of a rotation matrix is its transpose. That's not generally true, but it's true for orthogonal matrices. So we calculate it like this because transpose is a simple function, but remember that the way it works is really like an inverse matrix. So you don't really have to remember that. I just think it's mathematically kind of interesting. Anybody have any questions about that? Okay, well, yeah, before Wednesday, if you have the time, look at the course information on D2L and see if you can follow get those programs entered into your calculator. You're going to eventually want one for the compliance matrix and one for the rotation matrix. And then on Wednesday, we'll just make sure it's in everyone's calculators. So remember to bring your calculators to class on Wednesday. Okay? All right, that's all.